This is Robert Sapolsky, and you're listening to Father-Offspring Interviews.
Hello, everyone. Welcome back to Father-Offspring Interviews. Before getting into questions, we wanted to respond to a few things from some recent episodes.
Yes, respond is a nice euphemistic way of saying, pointing out two mistakes that I had. This was a number of weeks back when talking about the possibility that Tylenol, acetaminophen, plays a role in increasing the likelihood of autism occurring, women taking Tylenol during pregnancy. And I summarized one meta-analysis showing that a history of taking Tylenol during pregnancy caused an increase such that the acetaminophen history explained 18% of the variability in the data. And fortunately, Charlie Darmore noted on YouTube that I got that completely wrong. Rather than that being 18% of the variability explained by acetaminophen history, it was an 18% increase. So various statistics professors of mine are turning over in their graves. The second one was related to the same thing, which was a fair number of comments, people saying, okay, so evidence, maybe some weak, strong, whatever, for a role for Tylenol in increasing the likelihood of an autism outcome. Why were people taking Tylenol? Maybe it was because of the fevers, not because of the Tylenol itself. Did they control for that? And very artfully, I neglected to say, yes, in those massive meta-analyses that I referred to, not only did they control for fever, they controlled for chronic illnesses, they controlled for age, they controlled for ethnicity, they controlled for socioeconomic status in these studies. So it's clean in that regard. So something I should have mentioned.
Okay, getting into questions, we are starting with one from Ayana from Germany, who says, you've mentioned before that many behaviors exist to pass on genes, yet some humans have little or no reproductive desires. From an evolutionary or biological perspective, what mechanisms might explain this? Are there any examples in other species or of individuals that choose not to reproduce?
This sends us back to the topic of sociobiology, which we covered in great detail a while back. Remember its birth in the 1970s, vanquishing two bits of nonsense in the evolutionary biology literature. The first one, the notion that animals behave for the good of the species. They don't do that. They don't behave for the good of any population at large. They do it for themselves. Second, the Darwinian soundbite, incorrect, of survival of the fittest. And what we got to is much more than survival. It is passing on copies of genes of the fittest. What evolution of behavior is about is individuals who have optimized passing on copies of their genes. So we heard that there were three basic building blocks to how this plays out. First, individual selection, the whole notion that sometimes a chicken is an egg's way of making another egg, all of behavior being this epiphenomenal state to pass on copies of genes into your next generation. And thus, we've got all sorts of species of males duking it out for reproductive access. And this is a common theme. So, individual maximization of one's reproductive success by reproducing as much as possible. Second building block, kin selection. You are related to your relatives, and thanks to Mendel, we know one, why you resemble your relatives, two, why you're not identical to them, unless it's an identical twin, and three, how it is that closer relatives share more genes with you than distant relatives. And the logic there becomes you have a full sibling who likely shares 50% of your genes with you. And if you reproduce once, or if you forego reproducing and let them aid them in reproducing twice, that leaves the exact same impact. One equals one half plus one half. And what this begins to explain is the obsession of species after species with kinship, cooperation built along lines of relatedness. And the most dramatic example you can ask for is females putting enormous effort into raising not an infant who is unrelated to them, but their child who has half their genes in common with them. And this is where you see among baboons patterns of grooming, follow relatedness. This explains a ton. Third piece, then every now and then you see animals cooperating with each other, even if they're not relatives. And the key thing is you can get this cooperation and reciprocity in many hands, make the task light. This could be very advantageous as long as it is indeed reciprocated. So the third leg being reciprocal altruism, the fact that all sorts of systems have evolved for mutual cooperation with two big provisos there. First off, it's great to cooperate with someone where you're both getting the benefits. It's even better to stab them in the back and cheat on them so you get all the benefits. Second, and thus, it is very good to be on guard against someone cheating against you. So the evolution of cooperation, reciprocity, attempts at cheating, evolution of cheating strategies, evolution of strategies for detecting and punishing cheating. And this culminated, as we've heard, in tit for tat. Tit for tat explaining fish and explaining birds and social bats and all sorts of species, their patterns of cooperation. So now we get to this question, what about humans? How much do we fit into this grand trio of predictive models, individual selection, kin selection, and reciprocal altruism? And the answer is we look great. We fit with it perfectly. For example, individual selection. Humans attempting to maximize their own reproductive success and looking at indigenous cultures all across the planet, the single leading cause of males killing males is reproductive access to females. And just to give you an example of what individual fitness could look like in humans, current estimates are that there are 60 million people on this planet who are direct descendants of Genghis Khan, the most reproductively successful male of all time, one might guess. Okay, so plenty of evidence for individual selection. Kin selection, it's absolutely obvious. We've invented a type of kin selection that other species would just kill to get to use. It's so wonderful and kin selective, which is after you die, you typically leave your money to your relatives, not to strangers on the other side of the planet. And what studies have shown is exactly as one might predict, the amount left in one's will, inheritance, follows a gradation of degree of relatedness to that relative. So that fits perfectly. Finally, reciprocal altruism. Do humans do that? Yes, this is economic systems. This is bartering. So humans totally fit all these models of trying to maximize copies of your own genes through your reproduction, through helping out kin, or reciprocally interacting with someone unrelated to you and stabbing them in the back if possible. So that explains everything until you look closely. And then you start seeing the exceptions. And the first one is what was brought up in the question. There are humans who choose not to reproduce. They may choose for reasons of religious beliefs, celibate priests throughout 2 millennium. Shakers did not reproduce. They did not believe reproduction was something humans should do. And big surprise, they went extinct, I don't know, somewhere in the early 20th century or so. And then you see a remarkable finding that is going to have enormous impact in the decades to come worldwide, which is more and more women choosing not to have kids. The replacement rate, average woman needs to have 2.1 kids to maintain the population. And in 110 countries on earth, we are now below that level. And not a whole lot of that is due to infertility. There's no government that's restricting reproduction. The days of one-child policies in China are over with. What you see is more and more reasons why people are choosing not to have kids. So much for humans being ruled by individual selection flagrant exceptions to it. Kin selection, flagrant exceptions. Adoption, blended families. And you look at families there made up of individuals whose degree of relatedness are virtually random if you adopted them from some distant continent. Or look at the American military in World War II, because the US is a nation of immigrants. You got troops during the war there made up of soldiers from gene pools, ethnic differences scattered all over Europe, scattered over Asia, and you got the unheard of, never in history possibility that in some trench punching it out there, American troops fighting against Nazi troops, you, some German American, are more likely to give up your life for the Polish American guy next to you than the fact that that guy over in the trenches, that German, is a third cousin, showing just how much humans can violate classical kin selection along lines of relatedness and to instead follow lines of pseudo kinship, feeling like it's a band of brothers. Finally, reciprocal altruism. We are willing to cooperate if somebody reciprocates back, but just consider the following scenario. You are in some foreign country, you're about to leave, you're going to the airport. The odds are you were never going to set foot in that country again. And you go in, and as you've opened the door, you pause for a second and you hold the door open for the person behind you. You are never going to see them again. You are never going to enjoy the benefits of reciprocity from them. We do all sorts of altruistic stuff that does not follow a strict economic model of reciprocity and symmetry. What are we seeing here? So you got humans with flagrant violations of all of the building blocks of the evolution of social behavior. What are we seeing? We're too damn smart of a species to be constrained by stuff like that. And you don't see exceptions like that in other species. You don't see a whole lot of celibacy in mongooses or lemmings, and certainly not mired in theology or ideology. We're the only species, and we have a theme we've gone through a lot of times. We are smart enough that as a species, we are freer from our genes of any other species on Earth, more subject to environment, more subject to culture. As a minor detail, we are freer from our stomachs than any species on Earth, which is why we populate all over the planet. We can eat anything, we could digest anything. We are the ultimate generalist species. And what that winds up telling you here is, yeah, there's strict models, predictions as to what human reproductive behavior, cooperative behavior, kinship behavior should be like, but we are too smart and too idiosyncratic to follow those rules. We only have vague trends towards following them.
Now, Gabby from Brazil asks, what comes before the turtles?
I love this question, this philosophical question. What comes before the turtles? What is being alluded to here in this recent book of mine, Determined? I started off beginning to make an argument that there's no free will with the following anecdote, the tale of the turtles all the way down. So here's how it goes. It seems that William James was giving a lecture about the nature of the universe. Afterward, an old woman came up to him and said, Professor James, you have it all wrong about the universe and Earth. Earth is on the back of a giant turtle. And James said, Okay, but madam, where does that turtle stand? And she said, On another turtle. And indulgently he said, But madam, where does that turtle stand? And she says, It's no use, Professor James, it's turtles all the way down. And the starting point is that sounds ridiculous. Why did this happen? Because of what preceded it. And that happened because of what preceded it. Turtle before turtle before turtles all the way down, infinitely down. That sounds ridiculous. And the point I make starting off this whole argument against free will is that may sound kind of ridiculous, but it is a lot more ridiculous to instead posit that somewhere down there, there's a turtle who could float in the air. And that floating in the air is what we call free will. So turtles all the way down. And here we come with Gabby's really tough question there of so what comes before the turtles? And I think what this sends us barreling to painfully is we're getting to the Big Bang. And God help us, we're getting to before the Big Bang. And I am not going to touch that one with a 10-foot pole. I am chickening out on that part of Gabby's question. Let's restrict ourselves to the first microsecond after the Big Bang, when the first turtle somehow began. And what we now have is wrestling with what is called Laplace's demon. Laplace, 18th century, I think, French philosopher who speculated if there was an infinitely knowing entity, infinitely knowing, which came to be called Laplace's demon, that could know the location of every single atom in the universe right now, that demon would be able to predict everything that will go in the future till the end of the world and could tell you everything that happened beforehand. And in this view, we're not talking about determinism. We're talking about some variant on Calvinist predeterminism. The notion that, yeah, by 1 second after the Big Bang, it was already all set in stone. And this is hugely incorrect and hugely dangerous sociopolitically, because if you believe everything was already determined, whatever is going to happen was already determined way back on the first turtle's toenails, what you're saying is nothing can change. So don't bother, which winds up being a fantastic excuse for system justification and supporting the status quo. It's not the case. What we have learned in recent decades is it is a deterministic world, not a predeterministic world, which is to say, right now, at this instant, there are multiple possible futures. Why is that if you know where every single particle is? And here we get to chaoticism, to nonlinear systems, to butterfly effects, sensitive dependent on initial conditions, attraction to strange attractors, all of that. What we have there is the science, the formal science of chaoticism as to why the future is not predictable. It was not set in stone back when, because chaoticism guarantees it is formally unpredictable. So there's multiple possible futures at this point. Whenever, whatever future it is winds up happening, your responses to it will have been determined by the turtles that explain how you became the individual who you were at that moment. So it's turtles all the way down, but I don't think it's possible there's a before the turtles, but I don't really want to deal with that. And most importantly, even if it's turtles all the way down, that doesn't mean the future is already set in stone and unchangeable.
Finally, Brian from New York says, can you explain how progressive MS happens and who is most vulnerable? Can it be prevented or is it inevitable, yet we can activate it sooner? My friend Danny has it extremely badly and blames himself for getting it, so I'm hoping he can have some closure.
MS, multiple sclerosis, yet another disease you don't want to get. Multiple sclerosis, the most common autoimmune disease of the nervous system that there is. It's one where your muscles begin to weaken, coordination begins to go down the tubes. Very often there's loss of vision, cognition slows down and becomes cognition's equivalent of being uncoordinated. People ultimately die of things like chronic obstructive pulmonary disease, heart failure, things of that sort. Now, the whole course of MS in someone is highly idiosyncratic. In some individuals, it comes on and it's there forever and remains steady. In others, it comes on and gradually gets worse. More common is it comes on episodically with periods of relapse into it, where the relapses either stay as constant or over time they get more severe. All of these idiosyncratic patterns. What seems to explain onset? What seems to be predictors of onset? Stress is one of those ones that increases the odds of a relapse. Having a family member with the disease is a predictor of it. Having any of a number of other autoimmune diseases. What other risk factors? If you smoke, that causes about a 50% increase in your risk for MS. How about risk factors for a relapse after you've been free of MS for a number of years, free of these symptoms, or mostly free of them? What causes triggers, stress, alcohol, excessive amounts of exercise, wildly disrupted sleep, all sorts of logical usual subjects. Excessive exercise so that you're in the range of major stress. Typically gets people between ages 20 to 40. Most strikingly, like most autoimmune diseases, there's a large female to male ratio, about 4 female cases for every male case. It is mostly found in the Northern Hemisphere. There's about 1 million cases in the United States, about 3 million worldwide, very roughly 1 case for every 1,500 people. So, what's going wrong in MS? Where is it coming from? And to appreciate it, we need to focus in on 2 bodies of knowledge that you need to get a very quick intro to, and both of which we've had at some point or other previously, but 2 very pertinent ones. First one, related to the nervous system. You got neurons with their cell bodies and these long, long axons by which they communicate to the next neuron in line. And they do so by there being an action potential, a burst of electrochemical excitability at the start of the axon that goes shooting down the axon, resulting in this neuron talking to the next neuron in line, an action potential. Now, you look at some of our neurons and they are outlandishly big. They have outlandishly long axons like our spinal neurons, where a single neuron may have an axon that's multiple feet long. And when you look at the workings of the electrochemical events that underlie an action potential propagating down, you got an axon that's a foot long, and by all logic, the propagation should take about 4.5 weeks to get down to the other end. It's extremely slow because you got to activate the action potential here, which triggers it there, which triggers it there and there and there. And there's a long process. And what we have instead is this brilliant evolutionary solution to making action potentials shoot down axons a lot faster. What you have is glial cells, those other cells that are found in the nervous system, in particular, what are called oligodendroglia. Glial cells wrap around the axon, wrap around it like plastic around a wire. It insulates them. It insulates with this stuff called myelin, which forms a myelin sheath. It does not insulate the entire axon over its entire length. That makes it too hard for the action potential to jump from this end of the start of the myelin to all the way at the other end. What you have instead is gaps at certain intervals, nodes of Ranvier. And what happens is you get the distance right, and the action potential here jumps to the next node and jumps to the next node, jumps and jumps with what is called saltatory conduction. And any of you who grew up with kangaroos as pets will know that saltation is hopping. It hops down the line. Okay, so myelin, very important. It is very important developmentally. Different parts of your brain myelinate at different points in time during your development. And we know so well by now the prefrontal cortex, the last part of the brain to fully mature around age 25, a big piece of that final maturation is finally myelinating all those axons in the prefrontal cortex. Okay, so we've got myelin sorted out now. The other piece, autoimmune disease. We've had this as well, but a review. What's the job of your immune system to attack things that are not you? Invasive things, invasive pathogens and parasites and viruses and bacteria, and to be really good at telling the difference between what is you and what is not you. And this insanely elegant thing goes on when your immune system has spotted something that it thinks is invasive, a bit of protein, the surface of the bacteria, whatever. And these immune cells called T cells begin to latch onto it and antibodies. And these go back to headquarters in your thymus gland and report what's going on. And you start to make antibodies and T cells that will recognize this thingy that you think is alien. That's fantastic. You start making tons of them, and then you've got two utterly elegant bits of quality control there. First off, you want to make sure that all these antibodies that you're making actually really do bind to that thing you spotted. So your thymus presents copies of that thing, and all the new antibodies and T cells filter past there, and the ones that don't bind to it well get killed, get sloughed off. So now you have a population that recognizes that alien thing. But you got to do one more bit of quality control. You got to make sure that this antibody recognizing this alien foreign thing doesn't just by chance happen to be recognizing a piece of you that looks like that alien pathogen, that it is not accidentally starting an autoimmune attack on you. So there's a second filtering that now goes on where the thymus puts up bits and pieces of all sorts of markers of you, and all the new antibodies and T cells filter past, and any that bind to it is one that's going to start an autoimmune disease. Get rid of it, destroy it. And through this process of what's called positive and negative selection, like 97% of the T cells that have been formed in response to this pathogen wind up getting killed. Programmed cell death that's normal. It doesn't cause inflammation, just to keep things under control. So you are now releasing antibodies that will recognize this invasive thingy and not accidentally recognize any part of you. So putting those two pieces together, what goes wrong in MS? It's an autoimmune disease where you accidentally form autoantibodies that attack the myelin in your nervous system. In particular, most often a protein called myelin basic protein, which is one of the anchors, one of the Velcro things that holds the myelin wrapping together. It attacks there and begins to destroy that and begins to destroy the myelin as a whole. And it begins to unwrap and it dies, and you get these sclerotic plaques from where things are rotting. And at that point, what do you know? You're doing this to some of the longest neurons in your body. Muscle movement, muscle coordination is not working very well anymore. Muscle weakness, and more importantly, lack of coordination because stuff is moving. This action potential is moving an eighth of a mile a week, and this one is moving a sixth of a mile a week, thanks to how much damage, and everything is uncoordinated, and it's a disaster. So that's what's going on in MS. You have an autoimmune attack on your myelin sheath, which causes demyelination throughout parts of your brain, throughout your spinal cord in particular. And this is where you get the muscle weakness, the discoordination, the slowing of movement, the slowing of cognition. That explains everything. So we got three things that we have not just explained. Number one, why are you forming autoantibodies against this myelin basic protein? Is there any pathogen your body ever encounters that's got some sort of surface protein that just happens to look a lot like that myelin basic protein, so that your immune system goes about its normal detecting of it and starting to make antibodies? And these are ones that, because of the similarity, are going to just happen to also key in on this myelin protein. Is there anything that does that? And the best evidence at this point is its infection with Epstein-Barr virus. About 90% of people have been exposed to it, and it seems to have a protein that cross reacts with myelin basic protein. You don't see it with some of the other viruses that lots of us carry, like cytomegalovirus. So that's the first step. Some sort of viral infection. It is not a slam dunk in terms of Epstein-Barr, but it's the best candidate. Some sort of viral infection where you are targeting something that just happens to look like this constituent of your myelin. That's great. That doesn't explain anything now, because the next step is these new antibodies that are going to wreak havoc with your nervous system. They should be undergoing that positive and negative selection in the thymus gland. All the ones that are accidentally recognizing your myelin, they should be getting filtered out and destroyed. So we got a second problem. Something about the negative selection fails. So, first problem, you encounter some alien protein, in this case from this virus, that just so happens to look like part of you, and you start making antibodies against it in T cells, and the quality control fails. So that's the second step. Final step. So now you've got all these autoantibodies that are going to target myelin basic proteins inside your brain. They normally don't get into your brain because of this thing called the blood-brain barrier, which keeps out all sorts of stuff, most famously immune cells under most conditions. So you got to have a third problem, which is some sort of breakdown of the blood-brain barrier. So some of these autoantibodies can leak in and begin to attack your myelin, either by that way or by way of your cerebral spinal fluid, which goes into a series of fluid-filled caverns in your brain. You tend to see the most sclerotic plaques surrounding these canals inside your brain. So what we see here is a lot of stuff needs to go wrong. You got to be infected with something that has something that looks like something in you that you really want, and where you accidentally jumpstart autoimmunity. Then you've got to have quality control fail in your immune system, and these things get into your circulation. And then you've got some sort of breach of this blood-brain barrier of yours, so it could finally access the cells where it's going to wreak havoc. And you put all these pieces together, this multi-step process, and this is where you get in trouble. Okay, so why some people more than others? And at this point, in addition to those risk factors, what is best implicated is some genetic profiles are more prone towards these mistakes, generating that particular autoantibody, having negative selection fail, having breaches of the blood-brain barrier, predominantly genes related to the quality control at the thymus gland. And what you see in those cases is these are not mutations. These are just part of highly variable families of genes called major histocompatibility complex genes, and certain assortments of them, certain orchestrations of them put you more at risk for this going wrong than in other people. In other words, there's a genetic component, but it's genetics of vulnerability. Twins, identical twins, one of them has MS. There's only about a 30% chance the other one will. That's way below what one might expect. So you see genetic vulnerability comes into it, coupled with all sorts of multi-step kicks in the rear where something goes wrong at multiple levels, which brings us back to Brian. And you're reporting that your friend Danny blames himself for getting MS. Unless he's got ways of turning up or down the throttle on negative selection in his thymus gland, or what sort of viral proteins get spotted, or how good his blood-brain barriers, there's no basis of blame at all. Brian, please tell this to Danny. Danny, please hear this. This is a disease that has nothing to do with anything you did that can cause it. It is completely independent of that.
And that is episode 86. I'm Offspring Sapolsky, and thanks for your continued support of Science and the Beard.